first speaker is Utkarsh. So please take it away.
Hi everyone. Can you all hear me?
Yeah, we can hear you. Yeah, fantastic.
Okay, so I just shared a quick slide that I made. So my presentation was on a different method that we proposed for constraining primordial non-Gaussianity. So I'll just go over what I presented in a quick one-slide summary. So we want to know whether our primordial universe had the fluctuations in the fields in the primordial universe, whether they were Gaussian or non-Gaussian. We want to know this because it's going to tell us a lot of interesting things about our primordial universe. There are many ways in which a field can be non-Gaussian. So we typically, the way we search is we look for theoretically motivated templates or signatures. And one such model or template is this local type non-Gaussianity that can be written as where the non-Gaussian field can be written as a Taylor expansion of a Gaussian field. And so the level of non-Gaussianity in this model is determined by this quantity FNL that we want to constrain. And people have constrained this in the past using CMB data, and we have found that this is very close to zero, but there's like an error bar on that, which we want to minimize using future large-scale survey data. And the best way of constraining this FNL is by looking at this large-scale scale-dependent feature that shows up when there is a non-zero FNL in the power spectrum of tracers like halos or galaxies. So this is the most promising method which LSS people, large-scale survey people use to constrain FNL. And this is going to give us a precision of order 1 in this decade. But the hope is to improve upon that as much as one can. And so, yeah, this is what motivated our work. And so the way this feature appears has to do with the fact that a presence of a non-zero FNL ends up producing large-scale modulation in this local sigma 8 quantity. So local sigma 8 are like RMS fluctuations around a region, and you can have this vary from place to place. And this variation can, in a non-Gaussian universe, is modulated by this large-scale primordial mode. And this is what causes this scale-dependent bias to appear in the halos. But there's nothing special, unique about halos. If we were to estimate the sigma 8 local, we will find that this field itself has this modulation, which will produce this 1 by k square scaling. So our goal is to find a local, use neural network to estimate a pi field, which is locally estimating the sigma 8 throughout the simulation volume. So we do this, we train our neural network on simulations. And okay, so yeah, we get the training done. And as per our expectation, we do end up seeing this 1 by k square bias term in the large scale power spectra of this pi field that we learn. And then we use this to produce constraints on FNL, and we find that we are getting an improvement of greater than 3.5 compared to a matter plus halo-based analysis. So in summary, this halo-based analysis is kind of state of the art, but our approach is improving upon that by a factor of 3.
Okay, great. I think that's a great summary. Fantastic. Let's open it up to questions. So let me check the Slack. I don't see any hand raised yet. I'll just check the Slack channel.
There's a question from James, I believe.
Go ahead.
Okay, I'm just reading Slack as well. So the question was, in the comparison of posteriors between halos and your pi network, the constraint contours look similar, but halos just seem noisier. Should I interpret this to mean that your pi network is effectively performing the role of a denoised halo field for the purposes of estimating FNL?
Yeah, I think that's fair. I mean, it's a fair, effective statement that it is kind of giving you analogous field to the halo field, which has a lower noise. But I would call that sigma, the pi field, to be the more fundamental thing. So So what exactly is happening is that sigma 8 local is getting modulated, and because of that, halos end up getting formed or not formed. So halo field is sensitive to sigma 8 field, and the pi field that we are learning is also sensitive to the sigma 8 field. So the local sigma 8 is probably a more fundamental quantity, and halo field and the pi field that we learn is like manifestations of that quantity with different noise levels. And turns out that the pi field has a lower noise. So in that sense, yeah. So there's definitely a similarity, but yeah. So I would agree with what James is getting at. Yeah.
Great. Thanks, and thanks for asking my question.
I'm so sorry I didn't see that you were actually.
No worries.
That's great. We do have a few more minutes, but I don't see any other questions in the Slack. And please, someone. Andrew says her hand. Sorry, I just saw it.
And
yeah.
Nico was first. So Nico, go ahead.
Thank you, Angus. I was wondering, you mentioned that you plan to extend this work, including the baryons. So how do you plan to do that? Like what is going to be your choice to deal with baryons?
You mean choice of? So we would ideally be again training on a simulation which has baryonic feedback in it. So for example, camel simulation is a good example of that. The nice thing about our approach is that we do not need a big simulation volume. So we are only training the network on a local field of view. So small, camels, which has a very small volume, would work just fine. The bigger issue is that even with camel or with any baryonic simulation, we do not know how true the models are to the actual value. So there would always be that uncertainty unless we figure out a better way of figuring, better way of modeling baryonic effects. But again, the good thing about our approach is that even though there is uncertainty in baryonic physics, the significance of detection of FNL is not going to get biased by our approach. So it's very robust. So that's why the first word in our title is robust. It's robust to baryonic uncertainties.
Okay, thank you very much.
Thanks for asking.
Okay. I don't think there's any further question on Slack or here. Although I saw...
So there is like a couple of questions by Mehdi. If you want me to answer it on here as well.
Well, maybe just one of them. Yeah, just one of them very quickly. We have a couple of minutes.
Right. So
yeah, sorry. Yeah, I guess I got the answers on this. Like, unless you want to just repeat it. Yeah, I'm totally fine.
Yeah.
With it.
Okay.
Yeah, thank you.
If you're okay. Yeah. Okay.
Okay.
Thanks.
Then in that case, I would suggest that we move to Elena. Next speaker.
Hi. Yeah. Hi, everyone. Yeah, I'm going to share my slide. It's just a slide from my presentation. Can you see it? So my talk was about Mark-power spectra that are two-point function of a marked transformed field. And the way we transform this field is by taking the field and weighting each galaxy by a function that depends on the local density. And we found that if this function upweight galaxies in underdense regions compared to galaxies in high-density regions, then the corresponding Mark-power spectrum contain information beyond the power spectrum. And so our idea is that Mark-power spectra are easy to measure in galaxy surveys. They contain additional information from standard power spectra. So because of this, there might be very promising statistics to study cosmology with galaxy surveys. And yeah, I will stop here.
Thanks, Elena. Fantastic. I saw earlier a question on the Slack from James, which wasn't answered. So I guess, James, if you want to, I either read it myself or if you want to ask it yourself.
I can read it. Yeah, so I asked two questions. The first was, I guess, in this plot where you had the HOD analysis with the power spectra of multipoles and the HOD parameters. sorry, I don't have the slide down. Yeah, this one.
Okay.
Yeah, I was just wondering if you had seen any improvement from going to a smaller smoothing for the marks for the satellite parameters, since they don't seem all that well constrained by the marks compared to the power spectrum.
Going to small scale, like to define the local density.
Yeah, I guess.
Yeah, I'm not sure about this. It's really a 3D parameter space. We have 3 parameters that control the mark. It's really a complicated space where sometimes, it's good to go to smaller scales, but then to smaller R, but then also the exponent P and delta S needs to be varied. I didn't look at like fixing the exponent and delta S and vary R to if specifically help with the satellites. But I guess it's a complicated basically surface to explore. And so if you vary R, then you need also to vary P and delta S to get good constraints, basically.
Okay, thanks. And then I had one other quick question, which I'm not super familiar with this, but you had mentioned that the marks are capturing higher order information. And I was wondering if people had looked at PNG with this or not.
Primordial non-Gaussianity, I think, not that I know of, but I think it's something very, very interesting to look at with more power spectra, yes.
Thanks.
Great. I don't see any other questions on Slack. Yeah, I don't think so. Okay. Last question. So, Elena, so that's great work, but moving further ahead, like what would be the immediate next step for this?
Yeah, so what I'm working right now is to build a basically simulation-based inference framework where we basically want to forward our galaxy field and our Mark power spectra and do a simulation-based inference analysis using galaxy surveys. The problem is that it's not so trivial to model analytically Mark power spectra, or at least not the marks that are very interesting from the cosmological point of view. It's also very hard to compute, for example, covariance matrices. And so this simulation-based approaches seems better. So we are looking at those to really do a cosmological analysis with those.
So the idea is essentially that you want to avoid to compute the covariance. That's the main reason behind choosing SBI with respect to traditional likelihood analysis, if I understood correctly.
Yes, and also modeling the theory itself of the Mark power spectrum.
Mm-hmm.
Also because like these theories are, for example, we have an EFT theory for them, but it's valid only up to some scale depending on the redshift. These are not very small scales. So if we want to push the analysis to smaller scales, then we need to model everything directly from simulations.
Nice, thanks. Okay. Oh, Atnea has a question.
Yeah, just a short question. Perhaps I missed, how did you choose P1 here? So you're upweighting the lower density regions, but how do you choose by how much to upweight them?
We considered different parameters and different combination of them. And then we picked the combinations of these 3 parameters that were giving better constraints on cosmological parameters. Yeah,
right.
so we did a search.
I'm sorry. If I remember correctly, you were looking at 0.5 as well, right? And 1. But what happens if you go to even further? I know 1.5.
For some, so for what parameters? Sorry, for P, the exponent.
Yes. For P.
Yeah. So if we go to very large values of P, then you are basically multiplying the density field by all these times, and then you're going to be basically the tail of the distribution of the density field become more and more important, but these are also the one that have more noise, and so you increase the noise and the measurements, then it's noise dominated, so we cannot really have larger values of very large values of P.
Right. So I guess for each data set, you have to check where you. Okay. Yeah.
Yes.
Thanks.
And one last question from Simon.
Hello. Could you say a little bit about the simulation-based inference framework that you mentioned right at the end of your talk?
Yes, sure. So basically, what we are trying to build are galaxy catalog that have also survey geometries and systematics of galaxy surveys. And then, so basically, we basically want them to measure the Mark power spectra in this galaxy catalog in the same way that we are measuring them from in galaxy surveys, and compare those with our simulation-based inference approach.
So, sorry, is this like an emulator that you're building, or are you doing some kind of likelihood-free inference? I guess is my question, really.
We are trying to do simulation-based inference, yes, not to build an emulator.
Okay, thank you.
Okay, I don't know if Andrews wanted to add something on the previous point. I think I saw a movement.
Yeah, but that's if we have time. I was just curious, so that I was interested in this discussion about the choice of P and that you modified or you selected that value so that you got the best cosmological constraints. I was wondering if there is is there an interpretation about why a particular value of P might be more sensitive to cosmological parameters, or is that just some nuisance parameter that you're marginalizing over effectively?
I guess that, for example, using perturbation theory, you can have a sense of why some of the parameters give better constraints. Because using perturbation theory, then you can work out really what kind of higher order statistics this mark contain, and have more of a sense of why some parameters constrain better cosmological parameters than others. But it's not that trivial, for sure.
Yeah. Cool. Oh, that's really interesting. Thanks very much.
Okay, we are pretty much exactly at the 10-minute marker. So I would say thanks again, Elena, and let's move on to Subranta.
Okay, thank you. So let me try to share my screen. Can you see the screen?
Yes.
Okay, perfect. So here's my 1-minute summary. So basically what I talked about in my talk is, so we came up with this new idea of a iterative emulator to speed up inference, cosmological inference. And to motivate this, one thing to remember is that when we are doing large scale structure analysis, say, for example, you're going to do LSST 3x 2-point analysis, which is what we are using as our example to illustrate why something like this is interesting. One thing to remember is that before going into the real data analysis, beforehand, you need to run many MCMC runs to test a bunch of different things. So for example, you need to check the impact of different systematics. You need to optimize what sort of observing strategy you're going to choose for your survey and so on. And all of these requires a very large number of MCMC runs. So of the order of thousands, for that matter, will be required for something like LSST. So you need something, and one thing to also remember is that each of these MCMC analysis, when you're taking a realistic assumptions on your model data vector, will require of the order of thousands of CPU hour, of the order of 10,000, I would say is a good ballpark number. So that means that the total CPU time that you need for just doing these sort of analysis is very large, of the order of millions of CPU hours. So you need a way to speed up these inferences. And there are many different emulators that has been built up to speed up such inference. But one problem that a most standard emulation technique will come up with at some point is that when you're trying to emulate in very high dimensions, it is hard. It's just the curse of dimensionality. One way to see this is this plot that I showed in the talk. It's a toy experiment that I did that, I took a large number of Latin hypercube parameters and tried to see how many points I need to get 50 points within the high posterior region. And that grows exponentially. So, it very quickly gets out of hand. However, you can just, solve this problem by coming up with an iterative emulator where you start up with a coarse emulator, and then you try to zoom into the high posterior region, because that's the only place we care about if our goal is to do cosmological constraint. So yeah, that's basically a reminder for what I did in this project. I'll be happy to answer other questions that might be.
Oh, thank you. Okay, great. Okay, Agne?
Thank you for a very interesting talk. I had a question. So you mentioned that this could be also used for example, assessing tensions. So is it right that this can also be used for calculating the evidence?
Well, we haven't checked this. This is on our to-do list, but my guess would be that checking evidence would be a hard thing to do because we are focusing on this local high posterior region, right? And again, like I'm not I don't know the ongoing stuff of tensions in very well, but from what I hear, like there are other metrics that you can use to assess tensions, and so yeah. So my guess is that for that sort of thing you can definitely use this sort of an emulator. Yes.
Okay, yeah, makes sense. I just wanted to double check.
Yeah, so the evidence question is there. That is on our to-do list, but yeah, I haven't gotten around to doing that yet.
Got it. Thanks.
Yeah, thank you.
Nico?
Yeah, well, first question is like, did you make slides with Angus? Because he also has, you have curse of the dimensionality, he has curse of the, was it covariance shift, right?
Oh, no.
No? Okay,
No.
my question is, I'm not sure, like, if I understood correctly, how did you deal with systematics in this case? Like, are you just...
So our emulator is a neural network. So I have like two different emulators, Gaussian processes and neural networks. I mean, dealing with systematics for our cases, it's just feeding in those parameters as input parameters to emulator, and that outputs the data vector. It's very simple, just that.
Okay, because I was like, maybe it's more complicated than, but
no, not really. So the only reason why, okay, so the thing that is different, I suppose, in what we're doing to some of the standard approaches is that we consider systematics as something like we do not do any different. We do not treat systematics as any different parameters. But the thing is that when you include the systematics in your emulation, that parameter space can be very high. And there you need to be careful about how you do the emulation, and instead of doing anything fancy by treating these parameters separately, what we are just saying is that we are going to choose our training sample such that we are just focusing on a small region of the parameter space, basically.
So like a trade-off, right?
Yes.
As usual, yeah. Okay. Thank you.
Yeah.
So there was a question. Andrews, sorry. Go ahead.
Hey, yeah, I have a possibly dumb question. If you generate an emulator that's designed to focus on the highest posterior density region, how do you ensure that the final samples and sort of posterior samples that you generate aren't artificially too clustered in the posterior space? So what I'm getting at is, how do you make sure that the marginal or two-dimensional posterior constraints have appropriate uncertainties? Is that a problem, or does that just sort of happen naturally when you do it correctly?
Sorry, so just to make sure, so are you saying that is the question basically that does have getting correct 2D posterior ensure that your higher like the higher dimensional posterior is correct? Is that the question?
It's a simpler question. I'm basically asking whether you trust your error bars.
So okay, there are two ways to answer this. In the exact case that we were doing, Yes, we do, because we have compared with a full MCMC run. Now the question is, do we need do we know that, you know, if I don't have a corresponding MCMC run, which is going to be the use case for the simulator, do we trust this? And yeah, so there are ways that you can sort of ensure it by probably, you know, just checking it on a test set and so on, like some sort of things like that. There are different sort of convergence criteria that you can come up with, but do we really know it without testing with the full posterior? I don't know. I'll have to think about it. But my guess is that you'll have to define some sort of a convergence criteria based on, you know, by checking what, let's say, if you have a delta chi-squared criterion or something like that. So you need something like that.
That'd be my guess.
But the other thing that you can very well do is that, you know, you can do it for you can take a few samples, calculate the importance sampling weight, and you can just, you know, like just apply that, and that should also be able to do that.
Yeah.
So
cool. Thanks.
Okay, great. Yeah, thanks. There was a question on the Slack by Jesus Torrado. Jesus is not here, right? So I'm just gonna read the question. Okay.
Yeah, I saw the question, but I
Okay. He likes in particular the detail of starting with a high temperature sampling for the training so that you can train into the emulator the rough picture. Okay, yeah, so he said they could not attend the discussion session. So in a typically fully trained emulator, for example, in the Gaussian process case, what is the dimensionality of the output space and how many training points or vectors in your case in particular are there? Do you take any approach to mitigate what he suspects is large size of the emulator, for example, the kernel matrix in the Gaussian process case, such as, for example, removing training samples containing redundant information, or is all of this not relevant because the size of the emulators is not a problem?
So yeah, I mean, so the question about what is the output dimension of the emulator, that's basically the size of the data vector that will depend on the exact use case. For our case, it's of the order of 1500. What that means is that, like, you know, for the case of Gaussian process, we have like one emulator for each data vector element. Like Gaussian process is not the best emulator in that sense. It's not like super, you know, fast compared to the neural network. But on the other hand, the usefulness of using a Gaussian process is that, you know, you can train your Gaussian process with fairly small number of data points. So in our case, of the order of 700, 800 data points was enough to get good posteriors with the Gaussian process emulator. And it's highly robust to the details of the training as compared to the neural network. I don't know if I missed anything. Was that the question? And regarding the mitigation of redundant samples, no, we do not do that. But I think that's a good idea in general, because more importantly, what happens is when you're sampling from the posterior, you have high density in the high posterior region and low density in the tails. What that means is the spacing between different points is different, which makes the training of the Gaussian process sometimes a bit you know, unstable around the tails. So so it's a good idea to do some sort of reweighting, but yeah, we haven't done that, and it works, so that's why we didn't care too much about it.
Okay, great. Thanks again. It's time to move to the next speaker. Thanks again, Supranta.
Yeah, thank you.
Jamie, it's your turn. Take it away.
Thanks. Can everybody see this?
I can see, yeah.
Okay. Yeah, so this is just a summary slide from the talk. I'll just give a really brief overview of what I said, which is basically presenting this new Boltzmann code that we have written in Julia. And the kind of goal of writing this, when we already have perfectly good Boltzmann codes, is to have one, a differentiable code, which can be useful for being able to do inference in high dimensions, and also to enable people to make more radical changes to the source code very quickly and easily. So yeah, the takeaways from the talk are basically that it's differentiable. We have checked it to the tolerance that seems to be standard for the agreement between CAM and class and other codes, which is to have it at the less than 0.1% level on the main observables, or at least for the linear power spectrum that I showed here. And then we also have been able to run it on GPU, even though that's still early days for that kind of thing. And no other Boltzmann codes have done that so far. Yeah, and the real point here is that we want to make a code that makes it easier for all of you to be able to go in and try whatever you want to try with minimal time spent debugging and editing source code.
Okay, thanks. Nico?
Yeah, thanks for very nice talk. Now, my question is immediately, how easily can this be implemented into existing pipelines, right? For example, I work PyCCL and Cosmology and Firecrown or whatever we have in Desk. How easy can I go for Julia? Because I mean, there's a lot of people also in the collaboration who are pushing for Julia and JAX, and even told me like, oh, you should try to use your code, you know, just convert it to. But like, how will it work? Well, what is your prognosis? I'm not saying that you have to say like, oh, it will work perfectly or not.
I mean, I will not say that it will work perfectly right off the bat. But yeah, I mean, for class and CAN and PyCCL, they're using the Python wrappers. We don't have a Python wrapper, but it would be very easy to implement one. There are some really nice tools for converting back and forth between Julia and Python that exist already. And I know they have their own set of, I don't know, input style and metrics for accuracy in CCL. So we would have to kind of conform to that set of standards, but I think there's like, it should be very easy to incorporate it into other existing frameworks. But right now the code is standalone. Yeah, I mean, you probably you work with Marius, right? So you people know what you're doing. But my question is true. Marius is great, but like, do you think that at one point we were all just going to like abandon Python or whatever? Well, if from my understand, Julia is more or less the same as Python, or it's just faster. So we can't really change the existing pipelines because I mean the servers are coming. So what would be your suggestion, like the road to take from your experience? I mean, I'm not really in a position to dictate what the whole field and all the big collaborations should do with their software stacks, but I mean,
you
I
have
really,
the right to opinion, no?
Yeah, no, for sure. I'm just trying to preface with the modesty. The thing that I would say is that for solving differential equations and for like the scientific computing aspect of it, which is really what the Boltzmann code is doing, I think Julia is for sure the best thing. Otherwise, we wouldn't have done this. But for like the other pipeline stuff, handling the data and passing stuff, I don't know. I think some amount of Python glue is definitely necessary. I don't think that Julia necessarily is better at that.
Yeah, I'm just asking because I have this piece of code that sorry, yeah.
Let's move on to the next question. And perhaps we can continue the discussion on the Slack. Sorry about that. Utkarsh.
Yeah, I have a very trivial question based on the JAX versus Julia culture war that I see on Twitter. Any specific reason for going with Julia instead of JAX? Or I'm not sure if this is a valid question even. So yeah.
Yeah, I'm scrolling back in my slides if you can see it. I mean, kind of for the reasons that I outlined, we went with Julia instead of JAX.
Well, sorry, I must confess that I did not watch your videos. I just, yeah, sorry about that. If you
no, it's fine. Yeah, but a little bit is covered in there, but I will just say really quickly that one thing is that Julia allows, by the way the language is designed for computing derivatives with automatic differentiation through anything really, whereas in JAX you have to have specific things like those qualifications on, you can't really use while loops unless they're structured in a very specific way, and like when you have an ODE solver that has a tolerance that you want to meet, you just evaluate until you meet the tolerance. You don't know this amount of iterations ahead of time. So that's one reason. Another reason is a lot of mature automatic differentiation and ODE solver libraries which even though Julia is not super widely used and super mature, those things are very mature and very well developed and highly benchmarked. So to keep it short, I will just give those two reasons.
Okay, let's move on to Supranta.
Yeah, no, thank you for the nice talk. So I have one question. So, so the idea behind trying to build all of these differentiable Boltzmann code and everything is that you can have everything, like the whole pipeline as a more differentiable form, and then that sort of helps you run your analysis faster. I mean that's at least that's the thing that I have in mind. Is that the case, or is there anything else why this is useful?
Yeah, I mean that's the most immediate
right. So
thing,
then
for sure.
Yeah. So then one thing that I have always wondered, and I haven't, I don't know what the solution to this is. So for example, if I want to use this for, say, doing weak lensing data vector modeling, I have to do a lot of integrations, and typically, like, the existing pipelines use, say, quadrature routines for doing the integration. That's just simple, and you need highly accurate integration as well. So, and you can't definitely use quadrature in this sort of a differentiable pipeline, right? I mean, at least I don't see how you do it naively. So how do you envision solving that? So, or do you see that as a bottleneck? Let me put it that way.
I guess I'm not really sure. Are you saying that you can't differentiate through the quadrature, or are you saying that that's a bottleneck no matter what in a differentiable
so
pipeline?
Yeah, can you do that? Actually, like, I'm not sure if there's an easy way to think about, because you have to do this very adaptively, right? Probably you can do that, but I don't know.
Yeah, you should be able. Here, like for our code, we have a fixed set of quadrature points, like for the master neutrino distribution integral, and we're differentiating through that. But I think that because of the way this is structured, I don't think there's any obstacle to differentiating through an adaptive quadrature solver.
Okay, let's close with the last question from Andrews, who will then be our next speaker. So can continue.
So I can eat into my own time. Fantastic. James, I have a question. I don't want to pit the host of this session against you, but I'm curious about your opinion of differentiable Boltzmann codes versus emulators. It sounds to me like a lot of stage 4 surveys are leaning heavily towards emulators for generating power spectra, because they are lightning quick once you have the training. And I'm wondering if you have a short, compelling reason why one might go with a differentiable Boltzmann code over an emulator.
There's a bunch of reasons. I don't know exactly what I want to say, but the first would be kind of this philosophical reason of wanting to enable model extensions and having the model extension only be limited by your imagination. Whereas if you're emulating, you're stuck with your training set. And, I mean, there was a great discussion, I think, in the previous session about reusing points when you're adding new parameters, but you do have to retrain those models. For like a pipeline that you have set up with an emulator and you're just changing the systematics parameters downstream, I think there's no way to beat the speed of the emulator. For speed, that is one of our goals with having the GPU capability, is to try and push speed for the actual ODE solves. So, I mean, I guess stay tuned for that. Right now, on one node, we're at like 2 seconds or something. So, but this is unoptimized, but we're at order of magnitude starting with the same time for CAM and class without any emulation. So, but yeah, that's definitely a goal, is for the speed to be faster, and it should be possible. Not to get as fast as just calling an emulator probably, but fast enough that it won't be noticeable. It won't be the bottleneck, maybe.
Okay, thank you very much. I would be really tempted to jump into the discussion here, but I will stop it here, and let's move on to Andrews for the final talk. Thanks again, James.
Yep. Thanks, everybody.
Great. Hi, everyone. So this is my little summary slide. I'm going to give you a very quick tour. So as you'll remember, I was talking about cosmic shear and stage 4 cosmic shear, and I showed you this sort of demonstration of why understanding redshift distributions is really important if you want to measure cosmic shear cosmology, because if you get the redshift distribution wrong, you get the cosmology wrong. So, you know, bad. And then I asked the question of, do our methods for that we use for stage 3 get us to within the requirements that are required for doing accurate cosmology with stage 4? And what I showed you in this plot was that no, they are not. And it turns out that the reason that they are not is because within a single pixel of a SOM that you use for calibration, the differing selection functions between calibration data sets and target data sets mean that you have this thing that's called covariate shift or prior probability shift, depending on which axis you're looking at. But the point is that they don't agree in their selection function, and that gives you bias. Let's discuss. Nico.
Sorry, yeah, I was just I was impressed by the beauty of your slide. Okay, Nitro has the first question.
Yeah, I might break the code of conduct, but like, because I'm the person responsible uploading everyone's talks, and I think the last 20 seconds of Angus's talk should be watched. So can you comment on that, or should we just let people, if they didn't have the time to watch that, maybe they can come back to you? But it was a fantastic experience as an organizer. Thank you for that. I'm still laughing like days after that.
I have no idea what you're talking about.
Okay. By the way, sorry, I don't want to corrupt unless he's going to really tell me. But where did you get this pictogram, like for the lenses? Did you draw that?
The cosmic shear, this one in the bottom right.
Yeah.
So this was a graphic that we produced here at the Ruhr University Bochum for a press release that Hendrik did. Hendrik Hildebrandt, my boss, did probably a year and a half ago. And then the lovely animations of moving the stuff forward and populating with additional halos, that was just me in Keynote.
Oh, okay, thanks. Yeah, and watch the last 20 seconds. Everyone should watch the last 20 seconds.
Yeah.
Okay, so I just want to ask a question about these 3 different failure modes. Are they actually different in any way? Because you said we can consider for the purpose of this talk as essentially having the same effect. But can you elaborate on?
Yeah, I can indeed. So the different modes are, when you're doing something like a regression, they have very fundamentally different causes and very different effects. So I'm going to do something which I probably shouldn't do, but I'm going to draw on my notepad here. So the classic example is the concept drift is the catastrophic one. That's where you have some data vector X and you have something that you're trying to map to Y, and you have a training set which might look like, you know, these data points here, and you then fit a function to it in your machine learning regression, and it gives you a function that looks like this. And it turns out that the validation data set just fundamentally does not follow the same conditional distribution of Y given X. That is, that the validation data set you're trying to then inherit Y values from as a prediction actually follows that distribution, right? And so naturally your predictions are garbage, right? That process there, that's called concept drift, when the training set and the target set don't have the same conditional distribution of your observables and the thing you're trying to predict. The other 2 are a little bit more subtle, and the reason that I say they kind of have the same thing just in a different name is because the first one is, this is the circumstance where your training set in purple gives you this sort of regression fit in green, but your data occupy, say, your target sample occupy that distribution, right? So it turns out because your training data sit in in a region of the parameter space that isn't fully covering your target data set, you get catastrophically incorrect predictions for part of the data set. And that can be caused by two things. In this circumstance, it's caused because the density of target data looks like this, and the density of training data looks like that. And you end up with this difference in the probability distribution on the x-axis, and that's called covariate shift. It's a difference in the covariate variables. But you can get exactly the same effect if instead of having this difference on the x-axis, you have it because of a fundamental difference in the prior volume of the training of the target variable you're trying to train. And that gives you something that's called prior probability shift. But the end result is you get bias in some part of your sample. And that's really all there is to it.
Very detailed, thank you.
Thank you. I have to say, Andrews, I'm really amazed by your drawing skills on the
My colleagues usually screenshot me very unkindly whenever I do that. I actually bought an electronic notepad specifically so I wouldn't be drawing with a trackpad anymore. But unfortunately, it's turned off and sitting on the table over there. So it should have come better.
No, you did very well. Nitro.
So this covariance shift that you mentioned, is there any way that this can be used to our favor?
No,
No?
It's nothing but a nuisance. Basically, it's the ideal circumstance that you would be in is that the training set perfectly looks like the target set you're trying to sample, you're trying to to reproduce. But then if that were the case, then you would never have any of these complex methods that we use to try and calculate redshift distributions, because by definition, the training sample is the same redshift distribution as the target sample, right? So you would just use the training sample redshift distribution and you would go, well, I'm done, right? The only thing that happens when you have these differing selection functions is you misinterpret signals. And there's no benefit to it. There's no good thing about it. It's just a pain. And the frustrating thing is that it's always going to be there. The only thing is whether or not you can address it in some sort of a clever way. And that's what we're trying to do. We're trying to come up with different ways to address it. And that's why I spoke about sort of the three main ways that we try and address it, with either forward modeling, better statistics, or more complex methods.
Great. I would say, Simon, you have the last question of the session.
Right. Yeah. So is one thing? Can you hear me?
Yep.
Yeah. Okay. So one thing you didn't talk about. Would it be? Would contamination in the sample, like stellar contamination in the galaxy sample, be an issue as well? Would you be able to get rid of, I mean, I guess that will fall out in the clustering bias redshift measurement as well. And I guess my second question is, you showed that Euclid is going to suffer from this. Is the Roman Space Telescope going to be a little bit better? As I understand, it has moderately fewer systematics, or is it about the same?
Yeah, so good questions. For the first one, any differing selection function in the sample that you use for calibration and the sample that you use for science is going to create one of these effects. Now, that can be because the calibration sample isn't complete and is systematically incomplete in parts of the color redshift magnitude space. And that's what I was talking about here. But it's equally as pathological if the calibration sample is a perfectly clean galaxy sample, which because it's spectroscopy, it will be, and the wide field sample you're trying to do science with has stellar contamination, because that will contaminate the redshift distribution in a way that is not clear, because you'll end up with stars that sit in the color cells, and they give you a false impression that you have more galaxies in a color cell than you actually do, and that causes a misinterpretation of the redshift distribution. So yes, it's exactly the same effect. It's just taken it from a difference. It's instead of this one not being equal to this one, it's this one not being equal to that one. You know what I mean? For the second question, these selection functions generally creep in at the the more complicated sample, keep into the more complicated sample. Generally speaking, wide field photometric samples are simple selections. They're a magnitude-based selection, usually with a shape measurement attached on top. And a shape measurement selection is not super complicated because, you know, things get smaller as they go farther away in a fairly characteristic manner. But the selection of whether or not something is targeted by a spectrograph, observed with a spectrograph well, and then confidently redshifted is just crazy. I mean, those three selection functions are all very difficult. And the last one in particular, human confidence in the accuracy of a spectroscopic redshift, is almost unrecoverable. So generally speaking, these biases don't come from Euclid. They don't come from Roman. They come from the spectrographs that we use to generate the calibration samples.
That was a great ending to the session. Okay, well, I think we heard amazing thoughts, and I would like to thank again all of the speakers and the participants in the session. It was really enjoyable.